Betelgeuse is one of the most familiar stars in the night sky. It marks the right shoulder of Orion bright enough to notice without any equipment. It is also close enough that modern telescopes can resolve its surface as a real disk, not a point of light. For more than a century, Betelgeuse was treated as a well-behaved red supergiant. Its brightness rose and fell in a slow rhythm of about 400 days. That cycle looked stable enough to anchor models of how massive stars breathe near the end of their lives. Then, in late 2019, the pattern broke. Betelgeuse began to dim faster and deeper than its usual variations. By early 2020, it had lost a large fraction of its normal visible light, and the change was obvious to careful observers. Through large telescopes, the disk no longer looked uniform. One hemisphere appeared noticeably darker than the other, as if a faint veil were drawn across part of the star. It was not a flicker in a data table, it was a visible change in the face of a supergiant. This event became known as the Great Dimming. Ultraviolet observations with the Hubble Space Telescope showed hot material moving outward through the star's extended atmosphere. As that outflow cooled, dust formed, and the dust blocked part of the stellar disk from our view. The explanation made sense, and the star gradually brightened again. The strangest part was not the dimming, it was what changed after the light returned. Betelgeuse recovered its brightness, but it did not recover its rhythm. After the Great Dimming, the familiar 400-day cycle no longer dominated. A faster rhythm near 200 days persisted instead, holding on longer than many predictions expected. Another signal sat underneath these changes. Across long records of brightness, astronomers traced a broader modulation of roughly 2,100 days. That timescale did not fit cleanly within standard pulsation models for a single red supergiant. In this episode, we will follow the evidence that forced a rethink. First, what the Great Dimming did to the star's outer layers. Second, why the pulsation pattern shifted and stayed shifted. Third, what the long 2,100-day cycle implies about the system Betelgeuse actually belongs to. This is not a story about an imminent explosion. It is a story about a nearby star that stopped matching its own history, and about the measurements that show it in plain sight. Betelgeuse is not simply a large star, it is a structure so vast that ordinary comparisons fail quickly. If it replaced our Sun at the centre of the solar system, immersed in hot, diffuse plasma, its radius is roughly 700 to 900 times travel from one side of the star to the other. What appears from Earth as a steady orange point is in reality a swollen sphere of gas larger than the inner solar system. Volume tells an even more dramatic story. Betelgeuse contains hundreds of millions of times the volume of the Sun. Yet despite that immense size, its mass is only around 15 to 20 times greater than our star. This imbalance between size and mass reveals something important about its structure. Red supergiants are diffuse. Their outer envelopes are extended and relatively low in density compared with smaller stars. Gravity is weaker at their surfaces because the mass is spread across such an enormous radius. This allows the atmosphere to expand outward, forming a vast envelope that is only loosely bound. Inside that envelope, energy is transported by convection on a scale that defies intuition. On the Sun, convection cells are small compared with the solar radius. On Betelgeuse, a single convection cell can span a significant fraction of the stellar surface. Some models suggest that only a handful of giant cells dominate the visible disk at any given time. These convection cells are regions where hot plasma rises from deeper layers, cools slightly at the surface, and then sinks again. The process is slow and powerful. Material can take months to complete a full convective cycle. The surface brightness pattern shifts gradually as these enormous currents evolve. This convection is tied directly to the evolutionary state of the star. Betelgeuse has already exhausted hydrogen in its core. For millions of years during its earlier life, hydrogen fusion provided steady outward pressure to counter gravity. Now the core fuses helium into carbon and oxygen. Helium fusion occurs at higher temperatures than hydrogen fusion. The core contracts and heats as each stage of nuclear fuel is consumed. Outside the core shells of hydrogen and helium fusion continue in layers, adding complexity to the internal structure. The result is an onion-like arrangement of burning shells surrounding a dense central region. Because the core contracts while the envelope expands, the star becomes cooler at the surface, even as it grows brighter overall. That is why Betelgeuse glows orange-red rather than white. Its surface temperature is only around 3,500 Kelvin, much cooler than the Sun. The cooler temperature shifts most of its radiation toward the infrared. Despite its relatively cool surface, the total luminosity of Betelgeuse is enormous. It radiates tens of thousands of times more energy than the Sun. This energy output drives a persistent stellar wind that carries material away into space. Over time, that wind removes significant mass from the outer layers. The combination of high luminosity and low surface gravity makes the atmosphere unstable. Gas can be lifted outward by radiation pressure acting on atoms and dust grains. Once material reaches sufficient distance from the photosphere, temperatures fall low enough for molecules to form. Farther out, still microscopic dust grains can condense. All of these processes occur within a system that is only about 650 light-years away. In cosmic terms, that distance is remarkably small. It allows interferometric telescopes to resolve the star as a disk and detect asymmetries across its surface. Few other red supergiants can be studied with this level of spatial detail. The proximity also means that subtle changes in brightness are easy to monitor. Professional observatories and amateur astronomers alike have tracked its variations for decades. Long records reveal repeating cycles, irregular fluctuations, and occasional dramatic departures from the norm. These datasets provide a laboratory for testing models of late-stage stellar evolution. Betelgeuse therefore occupies a unique position in astrophysics. It is massive enough to end its life as a core-collapse supernova. It is evolved enough that internal fusion has progressed beyond hydrogen, and it is close enough that we can observe surface structures and atmospheric behavior directly when we describe it as a dying giant that phrase compresses an enormous amount of physics. Gravity pulling inward, radiation pushing outward, convection, redistributing energy, nuclear reactions forging heavier elements. Each of these processes operates simultaneously, interacting across scales from the core to the extended envelope. To understand the later mysteries surrounding its dimming and shifting pulsations, we first need to grasp this physical foundation. Betelgeuse is not a simple glowing sphere. It is a vast, unstable structure balanced between collapse and expansion. Every change we observe at its surface is rooted in the extreme conditions deep within its interior. In September 2019, Betelgeuse began to look slightly off to observers who knew its usual glow. At first, it seemed like an ordinary dip within a familiar cycle, but week by week the star kept fading, and the decline did not level out. By October, the change was obvious in careful brightness estimates. By November, reports from amateur observers spread quickly, and professional teams began continuous monitoring. In December, the dimming crossed a threshold that made it hard to dismiss as routine. On February 7th, 2020, the visible light reached its lowest point. Betelgeuse had lost more than 2/3 of its normal brightness in the visual band. For a star that often ranks among the brightest in the sky, this was a startling fall. Because Betelgeuse is close and large, the event could be studied in unusual detail. Astronomers aimed many instruments at the star, from optical photometry to infrared measurements and spectroscopy. The key question was direct: did the surface cool, or did something block our view? Ultraviolet data provided an early clue. In 2019, months before the deep, visible fading, the Hubble Space Telescope recorded unusual activity above the photosphere. It detected hot, dense material moving outward through the extended atmosphere at very high speed. Those ultraviolet signatures pointed to an outflow, not a quiet change in temperature alone. A massive convective upwelling can rise from deeper layers, reach the surface, and carry hot plasma into higher altitudes. When such an upwelling breaks through, it can drive a short, violent ejection. Material pushed outward expands and cooling changes what the gas can become. Close to the star, many elements stay as a hot vapor. Farther out, molecules can form, and at still lower temperatures, some species condense into microscopic grains. Dust grains are small, but they interact strongly with starlight. They absorb and scatter light, especially at visible wavelengths. If a dust cloud crosses part of the stellar disk, the star can dim without the photosphere itself changing as much. That is what the best multi-wavelength evidence supported. Infrared brightness did not drop in the same proportion as visible brightness, which is consistent with obscuration by dust. If the surface had cooled uniformly, the infrared output would have fallen more strongly along with the visible light. Ground-based interferometry added a visual confirmation. High-resolution observations from the Very Large Telescope produced images that showed an uneven disk. One region looked markedly darker, as if a thin curtain covered part of the photosphere from our viewpoint. The simplest interpretation was geometric. A dense cloud formed along the line of sight to one hemisphere, on the order of a quarter of the visible surface in reconstructed images. The cloud absorbed and scattered light, reshaping the brightness curve seen from Earth. This was not a passive veil drifting in from far away. The evidence pointed to material that came from Betelgeuse itself. A convective cell, unusually strong, likely rose and helped launch the outflow that later cooled into dust. Once dust forms, radiation pressure can push it outward, and the dust can drag gas along. That coupling is one pathway for mass loss in red supergiants. The Great Dimming became a rare window into that process in real time. The event also had a clear sequence. Ultraviolet activity appeared before the deepest visible fading, consistent with hot plasma moving outward first. The strongest dimming arrived later, when the outflow had cooled enough for dust to condense and thicken along the line of sight. By March and April 2020, the star began to brighten again. That recovery did not require any change in the core. It required the dust to disperse, thin out, or move out of alignment with Earth. Dust clouds expand and fragment as they are carried outward by winds and radiation pressure. By mid-2020, Betelgeuse looked closer to its usual brightness. In a narrow sense, the episode was explained. A surface outflow and subsequent dust formation matched the depth, the wavelength dependence, and the asymmetric appearance. Yet the Great Dimming mattered for a deeper reason. It showed that Betelgeuse can shed material in episodic bursts, not only in a smooth, steady wind. Repeated bursts could change the outer envelope and the environment around the star in ways models still struggle to capture. Brightness changes in red supergiants rarely have a single cause. Surface temperature, pulsation, convection, dust, and viewing geometry can combine, and the observed light curve is their blended result. The Great Dimming forced that lesson into view. Most importantly, for what comes next, the event may have disturbed the star normal pulsation. Shocks and returning material can redistribute energy between oscillation modes. So the Great Dimming was not only a dramatic veil of dust, it may have been a shove to the whole system. That is why this chapter is more than a recap of a famous dip. It is the moment when a predictable rhythm was interrupted by an eruption we could document. The light recovered, but the star behavior did not fully return to its old pattern. In this story, the most important change is not how deep the star dimmed. It is that the star kept a different rhythm after the dust cleared. Some teams estimated the amount of condensed material by modelling how much light the cloud removed. Expressed in solar masses, it was tiny, but in familiar terms, it was a few hundredths of an Earth mass in dust and gas. For a few months, that is enough to matter. The nickname Stellar Sneeze captured the character of the event. Pressure and convection built toward a release, then a burst sent material outward, and the aftermath lingered as dust. The phrase is informal, but it points to something real. The star can lose matter in pulses. Observers also learned how valuable dense monitoring can be. Nightly photometry spectra across seasons and images at different wavelengths stitched the sequence together. Without that coverage, the dimming could have been misread as a simple temperature swing. With it, the event became a benchmark for how red supergiants can hide behind their own dust in plain sight. Before the Great Dimming, Betelgeuse pulsed with a steady rhythm that astronomers had tracked for decades. Its brightness rose and fell over roughly 400 days. That period was consistent enough to serve as a diagnostic of the star's size and internal structure. Stellar pulsation is not random flickering. It is driven by layers within the envelope that alternately trap and release radiation. When a layer is compressed, it heats and becomes more opaque. Pressure builds and the star expands. When it expands, it cools and becomes more transparent, radiation escapes, and gravity pulls the layer back inward. This repeating cycle creates a global oscillation known as the fundamental mode. In that mode, most of the star's envelope moves in and out together. For Betelgeuse, a 400-day period matched theoretical expectations for a red supergiant with its estimated radius. After the Great Dimming, that familiar pattern no longer dominated. Instead of 400 days, a shorter period near 200 days began to stand out. The star was in effect breathing twice as fast. A shift like that is not a small adjustment. Pulsation period depends on the density profile and effective size of the oscillating region. If the dominant period changes by a factor of 2 something, in the structure or the excited mode must have changed. One explanation involves the excitation of an overtone. In addition to the fundamental mode, stars can support higher frequency oscillations. These overtones involve nodes within the envelope where some layers move inward, while others move outward. In the first overtone, the envelope is divided into regions that are out of phase with each other. Material above a certain depth expands, while material below contracts, then they reverse. Because the effective wavelength of the oscillation is shorter, the period is shorter as well. The Great Dimming likely involved a powerful surface outflow and associated shock waves. When a large mass of material is ejected, pressure waves travel both outward and inward. Those disturbances can redistribute energy among different oscillation modes inside the envelope. If enough energy is transferred into the first overtone, it can temporarily dominate the brightness variations. That would naturally produce a period close to half the original fundamental value. Numerical models suggest that such mode switching is possible in evolved extended stars. However, overtones are usually less stable than the fundamental mode. They require a specific distribution of energy and can be damped by turbulent convection. For that reason, some researchers predicted that the 200-day period would fade within several years. Yet years have passed and the shorter period remains prominent. There are 2 clean readings here. One is that the envelope settled into a new preferred mode after the disturbance. The other is that something continues to nudge the star on a repeating schedule, preventing the old balance from reasserting itself. This persistence raises 2 possibilities. Either the damping timescale is longer than anticipated, or some mechanism continues to reinforce the overtone. Convection may play a role in sustaining the new rhythm. Betelgeuse's outer envelope is dominated by enormous convective cells. These cells generate stochastic fluctuations in pressure and opacity that can feed energy into oscillations. If the structure of the envelope changed during the mass ejection, the balance between modes might have shifted. The density gradient could have been altered enough to favour the overtone as the lowest energy configuration available. In that case, the star may have settled into a new quasi-stable state. Another factor to consider is the influence of the companion star. A secondary object moving through the extended atmosphere can generate periodic disturbances. If those disturbances occur on timescales that resonate with the overtone, they might help maintain its amplitude. Resonance does not require perfect matching of periods. Even approximate alignment between forcing and natural frequency can transfer energy efficiently. In a complex stratified envelope, small periodic nudges can accumulate over many cycles. Beyond the 200-day signal, additional variability appears in long-term data. Light curves reveal a broader modulation on the order of 2,100 days. This timescale cannot be explained by simple radial pulsation of a single star with Betelgeuse's measured radius. The coexistence of multiple periods complicates interpretation. Brightness at any moment reflects the superposition of several oscillations and surface patterns. Separating these components requires careful frequency analysis over many years of observations. This technique, known as astroseismology, treats the star as a resonant cavity. Different oscillation modes probe different depths within the envelope. By measuring their periods and amplitudes, astronomers attempt to infer the internal density and temperature structure. For Betelgeuse, the presence of a strong overtone challenges simple models. If the fundamental mode has been suppressed or weakened, that suggests a redistribution of mechanical energy inside the star. Such redistribution might reflect deeper structural evolution, not just surface phenomena. At the same time, uncertainties in radius and mass propagate directly into uncertainties in expected periods. Interferometric measurements of angular diameter vary slightly with wavelength. Converting those measurements into a physical radius depends on distance estimates that carry their own margins of error. Because pulsation period scales with the square root of mean density, even modest changes in assumed radius affect theoretical expectations. If the star is slightly smaller or larger than assumed predicted periods shift accordingly. This sensitivity makes the interpretation of mode changes a delicate task. The central question remains open. Did the great dimming simply excite a temporary overtone, or did it reveal that Betelgeuse's internal structure is evolving more rapidly than standard models assume? The answer will emerge only through continued monitoring and refined simulations. What is clear is that the star's rhythm is no longer textbook simple. The shift from 400 to 200 days transformed a predictable oscillator into a more complex system. Each pulse now carries information about shocks, convection, possible resonances, and the layered interior of a massive star nearing the end of its life. For many years, astronomers suspected that Betelgeuse might not be entirely alone. Long records hinted at a slow modulation lasting about 2,100 days. That timescale was difficult to reconcile with radial pulsation in a single red supergiant. The signal was subtle compared with the dramatic 400-day cycle. It appeared as a gentle rise and fall laid over shorter variations. Some researchers tied it to shifting convection patterns across the surface. Others proposed rotational modulation. Rotation in red supergiants is hard to measure directly. Their surfaces are turbulent and spectral lines are broadened by large-scale motion. Any attempt to extract a clean rotation rate must disentangle it from pulsation and convection. A companion star offered another explanation. If a smaller star orbited Betelgeuse with a period near 2,100 days, its motion could imprint a repeating pattern. Gravitational interaction might disturb the outer envelope, and the combined light could change by a small but measurable amount. Detecting a companion beside Betelgeuse is not straightforward. The primary is dazzling and its disk is large on the sky, so glare dominates nearby pixels. Trying to spot a faint neighbour is like trying to see a candle beside a stadium floodlight. For years, teams tried indirect routes. They searched in ultraviolet and X-rays, hoping a hot secondary would stand out where the red supergiant is faint. They used space telescopes and ground instruments, yet the suspected companion remained buried in the glare. To overcome atmospheric distortion, astronomers use speckle imaging. Instead of one long exposure, they record many very short exposures that freeze turbulence for an instant. When the snapshots are combined, a hidden point can emerge at a separation as tiny as a golf ball seen from several kilometers away. This approach was applied with the Gemini North telescope. In late 2024, high-resolution speckle observations revealed a faint point of light very close to Betelgeuse. Repeated analysis indicated that the detection was real, not a reconstruction artifact. At Betelgeuse's distance, the measured angular separation corresponds to several astronomical units. That scale is comparable to the region between Mars and Jupiter in our own system. It is still small compared with the reach of the star's extended atmosphere, which is diffuse and layered. Photometry suggests the companion is far less luminous than Betelgeuse. Its colour and brightness are consistent with a star around 1.5 times the Sun's mass. Such a star would be hotter and bluer than the red supergiant primary, and it would be named Siwaha in recent reports. The presence of this companion provides a natural explanation for the long modulation. An orbital period of roughly 6 years matches the slow cycle seen in brightness data. As the secondary moves along its path, its position relative to our line of sight changes in a predictable way. Betelgeuse does not have a sharply defined edge like a solid sphere. Its atmosphere extends outward in a diffuse envelope with gas and dust that can reach distances comparable to the companion's orbit. This means the companion may travel through the outer layers of that envelope rather than circling an empty space. Motion through tenuous gas should create disturbances. The companion can compress material ahead of it and leave a wake behind it, altering local density and opacity. When that disturbed region crosses our line of sight, it can act like a partial curtain and modulate the light we receive. This framing makes the 2100-day cycle feel less mysterious. Instead of an exotic pulsation mode, it can be the periodic signature of orbital motion plus atmospheric stirring. A long baseline of brightness data becomes in effect a clock that tracks where the companion sits in its loop. The discovery reframes earlier debates about rotation and intrinsic long-period variability. What once looked like a strange internal clock may instead be the orbital rhythm of a second star. Betelgeuse is not just a solitary giant, it is an interacting system on scales similar to the primary itself. Speckle imaging alone does not yet deliver a complete orbit. More observations are needed to trace the path precisely and to measure the companion spectrum with confidence. Future epochs when the separation widens will make confirmation easier. Those windows allow cleaner spectroscopy and tighter mass estimates for both stars in the system. Even so, the detection aligns closely with the unexplained 6-year cycle, and it changes how the star must be modelled. The fit is compelling, but the claim only becomes secure when multiple epochs trace a real orbit. Until then, it is a strong convergence of clues, not a finished measurement. When Siwaha moves through the outer atmosphere of Betelgeuse, it behaves less like a distant companion and more like a ship crossing a fog bank. The primary is not a clean-edged sphere. It is surrounded by an envelope of gas that thins gradually with distance. Inside that envelope, even a star can leave marks that instruments can detect. A red supergiant atmosphere is layered and restless. Close to the photosphere, the gas is dense enough to form molecules. Farther out, it becomes patchy. Radiation pressure, pulsation shocks, and convection driven flows keep the material in motion at many speeds at once. Siwaha does not pass through a uniform medium. It encounters clumps, streams, and temperature gradients, and its gravity pulls on them as it goes. Material ahead of the companion can be compressed, while material behind it can be rarefied, creating a wake that stretches along the orbital path. The wake matters because opacity matters. If compressed gas in the wake forms molecules or dust more efficiently, it can scatter and absorb a measurable fraction of starlight. From our viewpoint, the wake can drift across the bright disk of Betelgeuse, and the system can dim on a schedule set by the orbit. The shape of the wake depends on speed and sound. In the outer envelope, gas responds to a passing object with pressure waves, and those waves can steepen into shocks. A shock front can form a cone behind the companion, a pattern that carries information about local conditions. The wake is not fixed in place. As the companion advances, fresh gas is compressed while older disturbed gas spreads sideways and mixes with the ambient flow. The result is a moving structure that broadens as Siwaha crosses the disk. The simplest picture is aerodynamic drag. Moving through gas, the companion experiences a resistive force, and orbital energy is converted into heat in the surrounding medium. In practice, the situation is more gravitational than aerodynamic, because the companion focuses gas toward itself and excites shocks. This process is called dynamical friction. As Siwaha moves, it perturbs the gas, and the perturbed gas pulls back on the companion through gravity. The net effect is a slow drain of orbital energy similar in spirit to drag but mediated by a gravitational wake. Energy does not vanish, it is deposited in the envelope. Some of it becomes heat, some becomes kinetic motion in shock fronts and turbulent eddies. That deposited energy can help lift material outward, making it easier for gas to escape in winds or episodic outflows. Heating can also change chemistry. Warmer pockets can delay dust condensation, while cooler compressed pockets can help molecules survive longer. Small shifts in temperature and density can move the boundary where dust grains begin to form. The wake also changes the local pressure structure. Where gas is compressed, pressure rises and flows can be redirected sideways around the wake. Where gas is evacuated, cooler pockets can form, and chemistry can shift toward molecules that would not survive closer to the photosphere. On Earth, a boat wake spreads and fades. Around Betelgeuse, the medium is so tenuous that structures can persist, especially if they are refreshed each orbit. Because the orbital period is measured in years, repeated passages can imprint a long-lived pattern in the circumstellar environment. Geometry controls what we actually see. At some phases, the companion and its wake sit off the edge of the visible disk, and dimming is minimal. At other phases, disturbed gas crosses in front of the photosphere, and the same amount of material can have a larger effect on brightness. Friction and tides work together. Tidal forces arise because gravity is stronger on the near side of one object than the far side. In a diffuse envelope, tides can raise large-scale distortions that lag behind the companion's position, and that lag transfers angular momentum. Angular momentum transfer is the key to orbital decay. If angular momentum is carried away by outflowing gas or redistributed within the envelope, the companion can spiral inward. The timescale depends on density relative speed and the uncertain structure of the outer atmosphere. Even a small change per orbit can add up. If the companion loses a tiny fraction of orbital energy each pass over many thousands of years, the separation can shrink substantially. Models suggest that once a companion is embedded in an extended envelope, inspiral can accelerate as density increases inward. As Siwaha moves inward, the interaction becomes stronger. The gas becomes denser, shocks become more energetic, and heating becomes more efficient. At some point, the orbit can enter a runaway phase, where the envelope absorbs energy faster than it can radiate it away. This is the beginning of a common envelope episode. The companion and the core of the giant share an envelope, and orbital energy is spent trying to unbind that envelope. If enough energy is deposited, much of the envelope can be ejected into space, leaving a tighter binary behind. If not enough energy is deposited, the companion can merge. It can plunge deeper, transferring its angular momentum into the star's interior. A merger can spin up the remnant enhance, mixing and alter surface composition in ways that persist for millennia. The Betelgeuse system sits in a delicate middle ground. The detected separation is small enough that Siwaha plausibly travels within the extended outer layers, but large enough that a full common envelope phase is not yet inevitable. That makes the system valuable. It may be a snapshot of interaction in an early and relatively gentle regime. The companion may also influence pulsation. Each passage can introduce a repeating disturbance, a nudge that arrives on the same orbital schedule. If that nudge couples to a mode already excited in the envelope, it can help maintain a rhythm that would otherwise damp out. From a distance, this interaction shows up as patterns in lightened spectra. Spectral lines can shift as gas accelerates in the wake, and absorption features can deepen when denser material crosses the line of sight. Brightness changes can then be tied to orbital phase rather than to the star's internal pulsation alone. The interaction can also confuse other measurements. If wake-driven motions mimic rotation signatures, radio and spectral observations can be harder to interpret. Separating true rotation from moving surface patterns requires time series data and careful modelling. What matters most is that Betelgeuse is losing mass while it is being stirred. A red supergiant already sheds material through winds, but a companion can concentrate that loss into preferred directions. Instead of a smooth spherical outflow, the environment can become clumpy, asymmetric, and time-dependent. Clumpiness can set the stage for sudden events. If dense pockets grow, dust can form quickly, and a line of sight cloud can dim the star even if the photosphere has not changed much. In that sense, an orbiting companion can act like a hand stirring a pot, making rare conditions more likely to occur. That asymmetry affects the future supernova. The shock wave will expand into whatever structure the star has built around itself. Dense arcs and shells can convert kinetic energy into light, changing the brightness and spectra we would eventually observe. For now, the wake is a laboratory. It connects orbit dynamics, gas physics, dust chemistry, and stellar evolution in one nearby system. Each passage of Siwaha through the envelope is a small experiment run by gravity written into the light we record. When a star behaves oddly, one of the first instincts is to blame the present moment. Yet some oddities are fossils. They were planted by events long ago, and only now show their fingerprints. For Betelgeuse, the idea of an earlier merger is one of those fossil explanations, dramatic, plausible, and still debated. The merger hypothesis begins with rotation. A single red supergiant is expected to spin down as it expands because the same angular momentum is spread across a much larger radius. Many models therefore predict very slow surface rotation, often so slow that it is difficult to measure cleanly. Betelgeuse, however, has been reported to show a faster pattern. Radio observations with ALMA have been interpreted as motion consistent with a surface speed of a few kilometers per second. That number is not extreme in everyday terms, but for a swollen supergiant it can be surprisingly large. Rotation is not just a curiosity, it changes structure. Centrifugal support slightly reshapes the star, and rotation-driven mixing can move chemical products between layers. Over time, that mixing can alter what the surface looks like in spectroscopy. This is where the second clue appears: surface composition. Some studies report that Betelgeuse shows more nitrogen at its surface than simple single star tracks would predict at this stage. Nitrogen can be enhanced when material processed by the CNO cycle is mixed upward from deeper layers. In an isolated star, that mixing can occur through convection and slow circulation. But a merger offers a more forceful route. It can stir the envelope violently and inject angular momentum at once. If Betelgeuse swallowed a companion earlier, it could be left spinning faster and showing chemical signs of deep mixing. A merger can also leave the star slightly out of equilibrium. The envelope may need time to settle, and internal flows can remain strong long after the collision. That residual turbulence can make variability harder to interpret, because pulsation and convection ride on top of a disturbed background. To picture the event, imagine a smaller star drifting inward as the primary expands. Once the companion enters the extended envelope drag, and dynamical friction pull it deeper, the orbit shrinks, energy is deposited, and the envelope can inflate and churn. In three-dimensional simulations, the plunge is messy. The companion creates shock spirals of gas and hot regions, where friction converts orbital energy into heat. Some gas may be ejected, while other gas is mixed inward and outward in the same episode. The angular momentum budget is central. The companion carries orbital angular momentum, and during in spiral, much of that momentum is transferred to the envelope. The result can be a remnant that rotates faster than a comparable single star. Mixing follows the momentum. As the envelope spins up, shear and turbulence increase, and that can dredge up processed material. Nitrogen-rich gas can reach the surface, while other abundance ratios shift in ways that can persist. If this happened, Betelgeuse today would be a survivor of violence wearing the scars as rotation and chemistry. It would also help explain why the star sometimes appears atypical compared with other red supergiants. A past merger would make Betelgeuse less of a textbook example and more of a special case. However, the evidence is not clean. The same observations that suggest rotation can also be explained by convection patterns. A red supergiant surface is dominated by giant cells rising and sinking on scales comparable to the stellar radius. Those cells create velocity fields that are not random noise. They can organize into large-scale flows, and when mapped at radio wavelengths, they can produce gradients across the disk. A gradient can resemble a rotating pattern, even if the star is not rotating in a simple solid body way. This is why some teams challenge the rotation claim. They run simulations with strong convection and no imposed rotation, then process the output as if ALMA observed it. In some cases, the synthetic observations look similar to the real maps, which weakens the argument that rotation is required. If apparent rotation is an illusion, one pillar of the merger case collapses. The nitrogen enhancement would then need another cause, such as mixing driven by convection pulsation or magnetic effects. Red supergiants are not simple, and abundance predictions carry uncertainties of their own. Even so, a merger remains attractive because it can explain multiple features at once. It can provide a natural source of extra angular momentum, it can enhance mixing, and it can reshape the envelope. It can also create a system that later acquires or retains companions in unusual configurations. There is also a demographic argument. Many massive stars form in binaries or higher-order systems. Interactions, exchanges, and mergers are therefore expected to be common, not rare exceptions. If Betelgeuse formed in a multiple system, a past merger could be part of a longer story. Two stars could have spiraled together, leaving a merged primary, while another companion remained bound at a wider separation. In that picture, the present companion Siwaha would be a remnant of the original family. This scenario connects the past to the present. A merger could explain why the primary is unusual, while the surviving companion explains long-period variability and atmospheric wakes. The system would then be a layered record of interactions across different timescales. The merger idea also affects the future. A spun-up star can have different mass loss patterns because rotation and mixing influence where dust forms and how winds are launched. If the envelope is asymmetric, ejected material can build arcs and clumps that later shape the supernova light curve. A merger can even influence the core. Mixing can change how fuel is supplied to burning shells and how the star evolves toward collapse. Small differences in structure can alter when later burning phases begin and how the final explosion unfolds. None of this means Betelgeuse is about to explode soon. A merger is a structural history, not a clock that sets an imminent deadline. But it would complicate attempts to estimate the remaining lifetime from standard single-star tracks. The strongest path forward is comparison. If other nearby red supergiants show similar rotation and composition, anomalies, mergers may be common. If Betelgeuse stands alone, then a special history becomes more plausible. Better data will help. A precise orbit for Suaha will constrain masses, and that will tighten evolutionary models. Improved imaging and spectroscopy can separate surface convection patterns from true global rotation. Time is also a tool. Convection patterns evolve, rotation does not change sign randomly, and a long monitoring campaign can reveal which is which. The star will not give up its history quickly, but patient observation can make the past more legible. For now, the merger hypothesis remains a powerful possibility. It offers a coherent way to link rotation chemistry and complexity without inventing new physics. It also reminds us that a bright familiar star can hide a chaotic biography beneath its steady glow. Another hint sometimes cited is the structured dust and gas around the star. Infrared maps show arcs and clumps suggesting mass loss is not perfectly smooth. Convection can do that, but a past merger could also have launched a brief dense ejection that is still moving outward. This is difficult to test because projection and dust opacity can mimic shells that are not coherent. For that reason, the merger idea is best treated as a working model, not a verdict. It tells observers what to measure next. Tighter abundance ratios, long baseline imaging, and rotation signatures tracked over time. If future data show global rotation and chemical anomalies, the merger case strengthens. If the patterns drift with convection, and the abundances fit, single star mixing the merger fades into a footnote. Above the detailed mechanics of orbit and wake, there is a quieter layer to this story. Betelgeuse does not change on human timescales in any dramatic sense. Its variations unfold over months and years measured patiently through repeated observation. Each night the star rises in the eastern sky during its season. Its orange light looks steady to the eye, no hint of shock fronts or compressed gas is visible. The complexity we have described exists beyond direct perception, hidden in data collected across wavelengths. Instruments extend our senses rather than replace them. Photometers register small changes in brightness. Spectrographs trace shifts in absorption lines. Interferometers map subtle asymmetries across the disk. Piece by piece, these measurements form a layered portrait of a living atmosphere. From a distance of hundreds of light years, the system appears calm. There is no visible spiral of gas, no obvious companion star shining beside the red giant. Only careful reconstruction reveals that another object moves within reach of the envelope. The wake it leaves is not a permanent scar. Gas flows refill evacuated regions, compressed pockets disperse, and dust drifts outward. What we see is a pattern sustained by repetition rather than by rigidity. This repetition is what allows astronomy to work. A single image might mislead, but a sequence over years can uncover cycles. When a 6-year modulation repeats with regular timing, coincidence becomes unlikely. The same patience applies to pulsation. A shift from 400 to 200 days is not confirmed in a week. It emerges only after many cycles are compared and analysed. Betelgeuse therefore teaches a methodological lesson. Understanding does not arrive in a flash. It accumulates through alignment of independent signals. Brightness curves, ultraviolet flares, dust signatures, and orbital hints must all agree before a new model is trusted. For now, the star continues to glow in Orion as it has for centuries. Its surface churns, its envelope expands and thins, and its companion traces a path we cannot see directly. What changes is not the star alone, but the clarity with which we can read the light it sends across space. When a companion moves within the extended atmosphere of a red supergiant, the interaction does not remain confined to the outer layers. Energy and angular momentum are exchanged gradually, and those exchanges can influence the deeper structure of the star. For Betelgeuse, this means the presence of Siwaha is not only an orbital detail, it is a factor in the star's long-term evolution. Angular momentum transfer is central to this process. As the companion travels through gas, it excites a gravitational wake that lags slightly behind its position. That lag creates a torque, and the torque removes angular momentum from the orbit, while adding it to the surrounding envelope. The envelope responds by redistributing that angular momentum. Some of it can be carried outward by stellar winds, some can be mixed inward toward deeper layers. Over many orbits, even a small transfer per cycle can alter rotation profiles within the star. Rotation influences mixing and mixing influences nuclear burning. When fresh material is transported into regions of active fusion, burning rates can shift subtly. Shell boundaries can move and temperature gradients can adjust in response. These changes are not abrupt, they unfold across thousands of years. Yet red supergiants evolve on comparatively short timescales in stellar terms. Small structural adjustments can therefore have noticeable consequences before the final collapse stage arrives. Mass loss is another key variable. Betelgeuse already drives a significant stellar wind-shedding material into the surrounding space. The companion's passage can concentrate that mass loss into denser arcs and streams, rather than a smooth spherical flow. An asymmetric wind alters how the circumstellar environment is built. Instead of a uniform shell, the star may surround itself with clumps, filaments, and partially detached layers. These structures can persist and expand outward, long after the disturbance that created them. The environment into which a future supernova expands is shaped in advance by this mass loss. If dense regions lie in certain directions, the explosion shock will encounter them at different times. The resulting light curve can brighten or fade in response to those interactions. This means the orbiting companion may indirectly influence how the supernova appears from Earth. The explosion mechanism itself depends on core physics, but the observed brightness and spectral evolution depend on surrounding material. A pre-shaped envelope can leave imprints on the light long after the core has collapsed. There is also the possibility of gradual inspiral. Dynamical friction in the extended atmosphere extracts orbital energy. If the density of the envelope increases as the companion drifts inward, that friction can strengthen over time. A slow inward drift does not guarantee a merger. The envelope density decreases with radius, and energy deposited by the orbit can be radiated away. Whether inspiral accelerates or stalls depends on detailed structure that models are still refining. If inspiral continues, the system could eventually enter a common envelope phase. During such a phase, the companion and the core of the giant share a single extended envelope. Orbital energy is then used to try to unbind that envelope and eject it into space. In some systems, the envelope is expelled and a tighter binary remains. In others, the companion spirals all the way in and merges with the core or inner layers. Both outcomes dramatically reshape the evolutionary path. For Betelgeuse, current estimates place the companion at a separation that suggests interaction without immediate catastrophe. The system appears to be in a relatively mild regime of envelope crossing rather than deep engulfment. That makes it an opportunity to study interaction before it becomes violent. Even without a full merger, the interaction can modify surface properties. Enhanced mixing can bring fusion products upward, altering spectral signatures. Slight changes in luminosity or radius can follow as equilibrium is re-established. The presence of a companion also complicates age estimates. Single-star evolutionary tracks assume isolation. If Betelgeuse has exchanged mass or angular momentum with a companion, those tracks may misrepresent its true stage. This uncertainty feeds directly into predictions about supernova timing. The onset of advanced burning stages depends on core mass and internal composition. If mixing has altered the core or shell structure, theoretical clocks must be adjusted. Yet it is important to keep perspective. Even with interaction, Betelgeuse remains hundreds of light years away. Its eventual explosion poses no physical threat to Earth. What changes is not safety but interpretation. When the star finally collapses, the light we see will carry the imprint of decades or centuries of prior interaction. Dense shells, asymmetric outflows, and stirred envelopes will shape the emerging radiation. In the meantime, continued monitoring refines our understanding. Orbital motion can be mapped more precisely, and spectral diagnostics can probe how gas responds to each passage. Each cycle of the companion becomes a data point in a long experiment conducted by gravity. The broader implication extends beyond one star. Massive stars are often born in multiple systems, and interaction may be the rule rather than the exception. Betelgeuse offers a nearby case where we can watch that rule in action. Rather than a solitary giant drifting toward collapse, it may be part of a dynamic partnership. That partnership transfers energy sculpts, mass loss, and possibly nudges internal evolution. The path to supernova is therefore not written by nuclear physics alone, but by orbital mechanics woven into stellar structure. When discussion turns to Betelgeuse and its future, the word supernova inevitably appears. A red supergiant of this mass is expected to end its life in a core collapse explosion. The uncertainty lies not in whether it will happen, but in when and under what internal conditions. Massive stars evolve through successive stages of nuclear burning. After hydrogen is exhausted in the core, helium fusion begins producing carbon and oxygen. Later stages can ignite carbon, neon oxygen, and silicon in shells around an increasingly compact core. Each stage proceeds faster than the one before. Hydrogen burning lasts millions of years, helium burning hundreds of thousands. Advanced burning phases can unfold in thousands, or even mere years as the core contracts and heats. The transition to iron is critical. Fusion of elements lighter than iron releases energy supporting the star against gravity. Fusion beyond iron consumes energy instead of producing it. When an iron core grows beyond a critical mass, it can no longer support itself. Electron degeneracy pressure fails and the core collapses in a fraction of a second. That collapse triggers the supernova mechanism. For Betelgeuse estimates of its mass range between roughly 15 and 20 solar masses. Stars in this interval are expected to undergo core collapse, rather than fade quietly into white dwarfs. However, determining the precise evolutionary stage is difficult. Surface observations do not provide a direct view of the core. We infer internal conditions from luminosity, temperature, composition, and pulsation. Each of these carries uncertainties that propagate into models. At times, speculative claims have suggested that Betelgeuse might be in a late carbon-burning stage and therefore close to explosion. Such claims often rely on specific interpretations of pulsation periods or luminosity shifts. Other analyses argue that the star is still comfortably within helium burning or early advanced phases. The discovery of a companion complicates these assessments. If orbital interaction has altered mass loss or internal mixing, single-star evolutionary tracks may not apply cleanly. Small differences in core mass can shift the timeline significantly. Despite this complexity, most current models do not place Betelgeuse on the brink of imminent collapse. Timescales of tens of thousands of years remain plausible within standard uncertainties. In stellar terms, that is short; in human terms, it is distant. When collapse does occur, the first signal would not be light. A burst of neutrinos would escape from the forming neutron star and reach Earth hours before visible brightening. Modern neutrino detectors are sensitive enough to register such a pulse from a star at Betelgeuse's distance. The visible display would follow as the shockwave reaches the surface. For weeks to months, the star could rival or exceed the brightness of the full moon. It would cast shadows at night and remain visible in daylight as a brilliant point. Because Betelgeuse is about 650 light-years away, the explosion would not threaten life on Earth. The flux of high-energy radiation would be diluted by distance. The event would be spectacular but not destructive. The remnant would likely be a neutron star. Depending on rotation and magnetic field strength, it could appear as a pulsar. Expanding debris would enrich the surrounding interstellar medium with heavy elements. Those elements include oxygen, silicon, calcium, and iron. They are forged in the final burning stages and in the explosion itself. Over millions of years, such material mixes into molecular clouds that form new stars and planets. In that sense, a future supernova connects back to the present discussion. Mass loss shaped by a companion dust created in episodic events and asymmetries in the envelope all prepare the stage. The explosion will illuminate the structure that decades of interaction have constructed. Yet the key point remains restraint. Betelgeuse has surprised observers with dimming and pulsation shifts, but surprise does not imply immediate collapse. A red supergiant can display dramatic variability long before its core reaches iron. The responsible stance is therefore cautious curiosity. Continue monitoring brightness spectra and orbital motion. Refine models with new constraints, but avoid tying every fluctuation to an impending end. When Betelgeuse finally explodes, it will do so because its core physics demands it, not because surface-like curves seemed unusual. Until then, the star remains a dynamic laboratory of late-stage stellar evolution. Its story is unfolding slowly, measured in cycles of years and decades rather than in moments of sudden catastrophe. In the public imagination, Betelgeuse often stands at the edge of explosion. Its recent dimming and shifting rhythms have encouraged speculation that the end might be near. Yet the scientific picture is more measured and more careful than those headlines suggest, to understand why it helps to separate surface behavior from core evolution. Brightness changes, dust formation, and orbital interaction all occur in the extended envelope. The timing of a supernova, however, is determined deep in the core where nuclear burning stages unfold. Current models place Betelgeuse in a late but not terminal phase of stellar evolution. Helium burning in the core or perhaps early advanced shell burning remains consistent with many observational constraints. These stages can last tens of thousands of years before iron accumulates at the center. The presence of a companion adds complexity but not necessarily urgency. Interaction can modify mass loss and mixing, yet it does not instantly accelerate nuclear reactions in the core. The timescale of gravitational stirring differs from the timescale of core collapse physics. Estimates of the star's mass radius and luminosity still carry uncertainties. Distance measurements, angular diameter modeling, and spectral interpretation all influence derived parameters. Small shifts in those parameters can change evolutionary tracks by thousands of years in either direction. Because of this sensitivity, claims of imminent explosion are difficult to justify. A star nearing iron core formation would show signs that are subtle and not easily inferred from light curves alone. Neutrino emission, for example, rises sharply only in the final hours or days before collapse. If Betelgeuse were truly on the verge, detectors on Earth would likely sense elevated neutrino flux before any visible cue. Such monitoring is ongoing, and no unusual neutrino activity has been reported. In the absence of that signal, models favor patience over alarm. When the collapse eventually comes, the event will unfold in a well-studied sequence. The core will implode, rebound, and launch a shockwave outward through the envelope. Within hours to days, the star will brighten dramatically as the shock reaches the surface. The light curve will then evolve over weeks and months. Interaction with circumstellar material, including structures shaped by winds and by the companion's wake, may enhance or modulate brightness. Spectral lines will reveal the composition and velocity of expanding debris. At a distance of roughly 650 light-years, the explosion will be safe for Earth. Radiation will spread over a vast sphere before reaching our planet. The event would be an extraordinary spectacle, not a hazard. The longer legacy will lie in enrichment. Heavy elements synthesized during late burning stages and in the explosion will join the interstellar medium. Over cosmic time, such material seeds new generations of stars and planets. In that broader view, Betelgeuse is part of a continuous cycle. Massive stars form burn-shed material and eventually explode, returning processed matter to space. Companions and interactions shape the details, but the overall arc follows established physics. The recent decades of observation do not overturn that arc. They refine it by adding nuance to how envelopes behave and how binaries influence mass loss. They also remind us that variability does not equal imminence. Astronomy advances by comparing prediction with measurement. As more data accumulate on pulsation modes, orbital motion, and spectral features, evolutionary models will narrow their ranges. Uncertainty will shrink, though it will never vanish entirely. For now, the most responsible statement is simple. Betelgeuse is evolving towards supernova as massive stars do, but the clock is not yet striking its final hour. Its shifting brightness is a chapter in a long story, not the closing line. When Betelgeuse finally reaches the end, the transformation will be sudden in human terms, but prepared by millions of years of physics. An iron core will form at the center, dense and unable to produce further energy through fusion. Without outward pressure from nuclear-burning gravity will win in a fraction of a second. The core will collapse inward at a significant fraction of the speed of light. Electrons and protons will combine into neutrons, releasing a flood of neutrinos that escape almost immediately. Those neutrinos will carry away most of the gravitational energy liberated in the collapse. For a brief instant, the inner core will stiffen under neutron degeneracy pressure and rebound. A shock wave will move outward, struggling against infalling material from the outer layers. If conditions are favorable, neutrino heating and hydrodynamic instabilities will revive that shock and drive it through the star. When the shock reaches the surface, Betelgeuse will brighten abruptly. Hydrogen-rich layers will expand and cool, producing the characteristic plateau seen in Type II supernovae. For weeks and months, radioactive decay of freshly synthesized elements will sustain the glow. At peak, the supernova may rival the brightness of the half-moon. It will be visible in daylight as a sharp point of white light against blue sky. At night, it may cast faint shadows and alter the familiar outline of Orion. Over time, the expanding debris will thin and fade. Heavy elements forged in the explosion, including iron and traces of even heavier nuclei, will mix with surrounding gas. The remnant will expand for thousands of years, shaped by pre-existing winds and by the structure carved by its companion. What remains at the center will depend on the final core mass. If the core is below a critical threshold, a neutron star will persist compact and dense. If it exceeds that threshold, further collapse may produce a black hole. Either outcome completes a cycle that began with gravitational contraction in a molecular cloud millions of years ago. The same physical laws that guided its birth will govern its death. No special exception applies to even the most dramatic stars. In that sense, Betelgeuse is not a cosmic anomaly, but an example. It shows how complexity arises from ordinary forces acting over immense scales of time and mass. Its mystery lies not in defying physics, but in revealing how rich that physics can be. Until the collapse occurs, observation continues. Brightness curves are measured, spectra analyzed, and orbital paths refined. Each data point narrows uncertainty and sharpens expectation. The final explosion will be spectacular, but the years of careful watching are equally important. They transform a distant red star into a comprehensible system governed by knowable processes. And in that steady accumulation of understanding, the true drama unfolds.